All right.
Yeah.
Ready? Okay.
All right,
Guys, I appreciate it.
We're ready to get started with the next one, so if you'll take your seats real quick. All right, Bob, you're up.
Great. Thank you very much. Okay, good morning, everyone. My name is Bob Cantrell, and what I'd like to do this morning is discuss a little bit of what Flex Power Modules is doing to further the 48-volt direct conversion ecosystem actually on the motherboard itself. So, you know, why did Flex Power decide to get into the 48-volt direct conversion? Basically, just to kind of step back, we've actually had been in direct conversion since the late 1980s. Starting off with actually the industry with actually full bricks at that time, which were the 48 to 5 volt direct conversion, and throughout the 1990s, the technology progressed from going from full bricks down to half bricks, quarter bricks, eighth bricks, 16th bricks, and today we are 32nd bricks. So the technology's been around for a long time. Even in the early 2000s, there were 48 volt to 1.2 volt bricks. So there was obviously the need for the lower voltage was identified years ago, about 15 years ago. But the efficiencies in those days at 1 volt were around the 82 to 83% level. So obviously today, the changes had to be made to even consider using a 48 volt bus to power today's silicon. Now the thing that really got us thinking about this was obviously back in 2016. Again, there's been many allusions this morning in different presentations about what Google had to say about going with a 48 volt conversion. Now, one of the things that's interesting is a quote from one of the senior VPs at Google. It's a good reason to have multiple versions of 48 volt racks to come up with a common standard. So we looked at that and decided that based on the R&D that was going on in our labs at that time, we could utilize technology that would benefit the 48 volt ecosystem to come up with a 48 volt to silicon voltage for direct conversion. So we started that same year developing products such as this. And one of the things, obviously, that the industry has to have is multiple sources. So you really need to have a multi-vendor approach. And to that end, we are one of the founding members of the PowerStamp Alliance, whose main charter is to provide standardized footprints and functionality for the 48 volt ecosystem. So the thing obviously driving the need for the 48 volts, as we all know, is the need for more data. More data equals more power. Looking at where the market is going today, you have big data, autonomous cars, which are extremely data hungry, and just the Internet of Things in general is really driving this market. It's driving the data. So there's an insatiable thirst for data, and consequently the power is increasing. Looking at today, you typically have 3 to 4 kilowatt motherboards, and 10 to 12 kilowatt racks are common. But again, as we saw this morning, in the next few years, those numbers will exceed 30 kilowatts, possibly even 40 kilowatts and higher. So there's a challenge of how do you best distribute a 12 volt along your board. Also, the thing that you have to look at is as there's more and more data needed and more power on the board, there's less real estate to do your power. So you have to have a solution that minimizes the power footprint as much as possible. So if we look at a typical, consider the typical system, as of today, you have a PIM module or power interface module or circuitry that is done discretely to accommodate the inrush current protection AB feeds. You have the need for Class B filtering quite often. So that is a common that you need to have on most boards. But today's quarter bricks are in the range of 1,000, 1,300 watts, and even going higher. So these products are already very efficient by the nature of getting that kind of power out of a quarter brick. So like in our case, we are at about 97.3%, which is excellent power. We also we'll be announcing, after we've announced at this show, we'll be having a switch capacitor product later this year that's going to be around 98.5% or higher. So, we see the importance of providing, two different alternate paths depending upon what the end customer really needs on their board and their overall application. Today, what happens is, obviously, the IBAs or the quarter bricks typically will provide all the downstream point of loads, or VRMs. You have the high power VRMs. You have reasonably high current point of loads for other ASICs and whatnot. And then you could, usually typically would have a dozen or more low voltage rails that are also powered off that 48 volt system. With direct conversion, what you do is just obviously go directly from 48 volts to your core voltage for the high current VRMs. And this is really a hybrid approach. You will end up needing like a 1/8 brick, a high current 1/8 brick, or even a 1/16 brick to power the non-GPU or non-processor power. But if you look at the efficiencies from a typical like a 97.5% front end or IBA, and like a 91% at 1 volt point of load, you're at about 89% efficiency. If you bump that up to 98.5 on a switch capacitor, and if you consider 92%, which is definitely state of the art for 1 volt, 12 to the 1 volt solution point of load, you're at 90% efficiency. So as I'll show you in a minute, the direct conversion, you're right out of the chute at 92% at 1 volt. So from a system architecture standpoint, basically what this is a scalable modular solution. It's a 6-phase design, and the power of the modules can vary, 70 amp, 100 amp, 120 amps. So basically, these modules will continue to increase in the power rating or current rating per module, just as the bricks have continuously increased in power. But what it does from a system standpoint, by having a modular system, you're actually future-proofing your power design. So, once your power design is established, you, at that point, can design for 1-2 generations ahead in the next version of processors or GPUs. You don't have to reinvent your power every time. And the other thing is, if you're early in the design stage with a processor, it might be unclear exactly how much power is needed. So what you can do is leave an open slot on your board. You can always add an additional module in case you need more power. And of course, we mentioned, obviously, you have an increased level of board efficiency. And one of the other things, too, is obviously you have complete PM bus control for telemetry, for monitoring, and also programming your module right on the fly. Here's the efficiency I spoke about, and this is important to consider. We use a dynamic phase shift with this solution. So what this curve shows, each of the blue lines indicates what the efficiency would be for a respective phase. For instance, at one phase, you'll see it peaks in efficiency at about 91.5%. 2 phases peaks at about almost 92%. Once you get 3 phases on out to 6 phases, you are at 92%. But this takes you out to 200 plus amps at a flat 92% efficiency. And what happens is you're looking for the phases keeping added, you have almost a straight line, almost a flat efficiency over to the usable part of the processor or GPU. And the other thing is through the interleaving of phases, you have an active current balance, which also helps really improve the thermal performance overall. You don't have hot spots. You have an equal power distribution across your board. The other positive byproduct with the resonant converter, which is what this is, besides increasing the efficiency, by having the zero voltage and zero current switching, you're able to have a very, very quiet noise floor. And for sub 1 volt processors, even getting down to like 0.6 volts, obviously having just a few tens of millivolts ripple can be very damaging to the operation of your processor. So in the case of this direct conversion with the resonant converter, we're in the neighborhood of plus or minus peak to peak 2 millivolts. So it's extremely quiet. And again, very important for the low voltage applications. And also, it also helps reduce the amount of capacitance you would need at the module because you don't have to worry about reducing ripple from the module. And the system benefits, it really comes down to two primary benefits. Obviously, the efficiency in a head-to-head, there's an improvement there. 2%, 3%, depending upon what you use as an overall architecture in your system. But the other thing is the elimination of those high current quarter bricks leads to board savings. And again, a lot of customers are telling us that maybe not necessarily today, but in the next generations of product, they are running out of room on the motherboard. So one customer had looked at their typical IBA approach with how many square inches of space would be needed. They compared it with the direct conversion solution, and they came up with a 56% reduction in board area. And that's major. So it's one of the things that, while efficiency obviously is very important, the main thing is, are you going to have room on your board to put power? It's kind of like oceanfront property. It's very, very rare. So that is one of the big advantages that this brings to the table, is that the elimination of a stage is critical from a space-saving standpoint. Of course, you're also looking at the advantages, again, of the scalability that you have with this kind of a system. So really, in conclusion, we are open and we're working together with the power community in order to facilitate a multi-vendor solution with compatible products for the 48-volt ecosystem for direct conversion. These are some additional links that you can look at for more information on the applicable documents from OCP and also for Flex Power Modules. And I want to thank you very much for your time, and thanks for coming out. Appreciate it.